So here we have the velocity measured at various times. The typical questions where we would want to ask are, what does the integral from 0 to 6 of the velocity, let's call that f of t, since it's not named in this one. What does 0 to 6 of f of t dt mean in this situation? And then we could estimate the integral with various approximation methods. Now, this is where we assume that the function is constant on a certain number of intervals, and the number of intervals we can decide on, or the number of intervals that we can have is based on the data that we're given. Here, we're given 4 points, so we could estimate with a number of intervals equal to 3, and that would mean that delta t is equal to 2. This is the information that we have. So, since we have an odd number of intervals, we could use the left endpoints. We could do the right endpoints. Or we could use the trapezoidal rule by averaging the left and the right endpoints. Remember the assumptions that we're making in each of these cases. In left and right, we are assuming that f of t is constant. And in the trapezoidal rule, we assume that f of t is linear on each subinterval. And then the trapezoidal rule assumes that f of t is linear on each subinterval. All right, so let's remember what the units tell us about what the interval means. So there's units all throughout this function. The velocity f of t is measured in feet per second, and the dt is measured in seconds, and we're multiplying these two quantities. So with the seconds cancel, the units of the definite integral are going to be in feet. The 0 and the 6 are significant as well. These are both times where t equals 0 to t equals 6, and t is measured in seconds. So the velocity is the rate of change of position. So the definite integral is the change in the velocity is the rate of change of position in feet per second. So the definite integral will be the change in position from 0 to 6 seconds. So let's see, the integral from 0 to 6 of f of t dt is the change in position in feet between 0 and 6 seconds. So the integral is going to be the net change in position in feet from 0 seconds to 6 seconds. Any questions? So the next calculation that we could make is to approximate this integral with the left or right endpoint approximations. So the left 3 approximation I'm going to use the left endpoints. This is going to be an overestimate because the function is decreasing. And so if I use the left 82 for this first 2-second interval, it's going to overestimate because the velocity is actually decreasing over those 2 seconds. So I'm going to take the 82, the 47, and the 12. Those are the left endpoints of the 3 intervals. The delta t is every 2 seconds. Since we're looking at rectangles and they all have a width of 2 seconds, we can just factor out the 2. And this gives us an approximation. So we'll get 2 times 82, 47, and 12. Any questions? The right endpoint will do a similar calculation, but instead of using the left endpoints, 82, 47, and 12, we'll use the right endpoints. So the right 3 approximation, the delta t is still 2, and now I'll use all the right endpoints. So there's a 47, a 12, and a 0. So in that first 2 seconds, the right endpoint is a 47. So I'll have 2 times 47, 12, and 0, which is 118. So based on this data where the car decelerates from 82 feet per second down to 0 feet per second in 6 seconds, that means the car traveled somewhere between 118 and 282 feet. This is not a very good approximation, as there's a 160-foot difference between the 2 estimates. So, and the difference between the 2 estimates is more than the lower end estimate. So that would be like, hey, what did I get on this test? Your score on this test was somewhere between 40 and 110 out of 100%. So they're pretty far apart. One thing that we could do is find the average of these 2, and that would make the trapezoidal rule. So the trap 3 approximation would just be the average of the left and right. That's one way to calculate the trapezoidal rule. So we'll just do 282 plus 118 divided by 2. We could also calculate the trapezoidal rule directly without the left and right. So to do that, we take the delta t and divide it by 2. That's the averaging part. And we're just adding the left and the right together. So we'll have 182. We'll have 2 copies of 47. We'll have 2 copies of 12. And 1 0. So scroll up. So we could also calculate the trapezoidal rule directly. If we have already been directed to calculate left and right, we might as well just average those 2. But if I led with just find the trapezoidal rule or use the trapezoidal rule to approximate, then we could make this second calculation. So we just take the delta t, 2, divided by 2 because the average. We'll have 1 copy of the 82, 2 47s, 2 12s, and 1 0. And there's the 200 again. So the 2's show up because we're adding the left and right together. So I can factor the two, but I have 82, 47, 12, plus 47, 12, and 0. There's two 47s and two 12s. In this particular case, we don't have enough information to do a midpoint rule. So since there's not enough information to do a midpoint rule, there's not enough information to do a Simpson's rule. In this case, there's not enough information to use a midpoint and therefore a Simpson's rule. Any questions? So we can see that the difference between the left and right approximations, 282 minus 118, is 164. So the difference between left and right is 164 feet. So left minus right is 164. Let's actually write out that calculation and see how the difference between left and right depends on how often we record the velocity. What does delta t have to be if I want the difference? How does delta t affect the difference between the left and the right endpoints? In the context of the problem, the difference is just how far what the range is of our underestimate and our overestimate. So this is just, we're saying this is estimating the distance traveled within 164 feet, which is not very good. So that raises it right now. If the delta t is between 2 seconds, we can say that the stopping distance of the car is somewhere between 118 and 282 feet. That is, the range of the left and right is 164. We are within 164 feet of the correct stopping distance, which is not very good because from 82 feet per second, you should be stopping in way less than 164 feet. I think this was described as a car. This is described as a car in the problem. Your stopping distance needs to be way less than 164 feet. Otherwise, you need better tires, better brakes, combination of both. Probably would help to make the car a little bit lighter as well. So but the information that we have, notice that the information that we have decreases very rapidly. This is a 6-second event, and we're only recording the data every 2 seconds. So our method of recording data is clearly insufficient. This is a 6-second event, and we only recorded data every 2 seconds. We recorded data every 2 seconds during a 6-second event. That's not a lot. There's clearly a lot going on. The car went from 82 feet per second down to 0 feet per second in those 6 seconds. So recording data every 2 seconds when there's only 6 seconds of data to record, that's not sufficient. That's why our gap is so large between left and right. So let's calculate the difference between left and right. Let's do left 3, this is the larger one. Let's calculate left 3 minus right 3. So left 3 is going to be the delta t, which is a 2, times the 82 plus 47 plus 12. And I want to subtract right 3, which is 2, times 47 plus 12 plus 0. Now, since the left of one rectangle is the right of another rectangle, I said that in the wrong order, the right end of one rectangle is the left endpoint of another rectangle. So we can see that I'm using the 47 and the 12 in both the left and right calculations. But the first one, the 82, is only the left of the first rectangle, and 0 is only the right of the last rectangle. So if I subtract these, the difference between left 3 and right 3 is going to be still the 2 seconds times the difference between 82 and 0. All the middle terms cancel out. That's what we want to observe here. All the middle rectangles cancel out when we're doing left 3 minus right 3. Everybody see that happen? Now, if we had more data, if we had, say, 12 subintervals, I would use 10 of them in the middle, or the 11 numbers in the middle. So if I did a hypothetical, so if n was 12 subintervals and the delta t was now a 0.5, because I take the 6 divided by 12 intervals, 0.5 seconds, rather than 6 divided by 2-second intervals for 3. So if n is equal to 12 intervals and delta t is 0.5 seconds, when we make the calculation left 12 minus right 12, when we subtract left 12 minus right 12, we would end up taking the delta t is 0.5. I'd have 82 plus 11 middle ones. And then I would be subtracting 0.5 times the 11 more in the middle plus the 0. So the 11 more, instead of just 2, like 47 and 12, there'd be 11 data points in the middle. And since we're looking at the difference between left 12 and right 12, the 11 in the middle would cancel out. And so left 12 minus right 12 will be the 0.5 times 82 minus 0. With left 3 minus right 3, 2 times 82 minus 0 meant a difference of 164 feet. If during those 6 seconds we only record the velocity every 2 seconds, our estimates of the distance is going, left and right estimates of the distance will be within 164 feet. That's not very good. But if we do left 12 and right 12, if we record the data every half a second, rather than every 2 seconds, now the difference between left and right will be only 41 feet. So we can see that the difference between left and right is proportional to the delta t. And so it's inversely proportional to the number of rectangles or subintervals. It's important to note the difference between left and right the two approximations that we're using, because that will be how close we could possibly be to the actual value. With only 3 subintervals, we're accurate to within 164 feet, which is not very good. With 12 subintervals, we've dropped that down to 41 feet. Notice that if we multiply the number of rectangles by 4, we divide the difference between left and right by 4. So the difference between left n and right n is inversely proportional to n. The difference between the left and right approximations is inversely proportional to n. That's because the delta t is inversely proportional to n as well. So the difference between left and right is inversely proportional to n, which means it's also directly proportional to the delta t. Any questions? So I could ask the question, how often would we have to record the velocity so that the difference between left and right is within 20 feet? So 12 intervals gave us a 41-foot difference. To be within 20 feet, I would have to use 24. That would get us down to 20.5. So I'd have to use more than 24. That would get us to 20.5 difference between left and right. Any questions?
You were talking about in proportional. That we see the difference from left to right is proportional, right?
Yeah, the difference between left and right is directly proportional to the delta t. Because it's delta t times the difference between left and right. Or sorry, the difference between left and right, if the delta t is divided by 4, then the difference between left and right is divided by 4. That's the direct proportion. It's inversely proportional to the number of rectangles. So if we double the number of rectangles, we cut the difference in half. If we quadruple the number of rectangles from 3 to 12, we cut the difference by a quarter. Any questions? All right, let's pause this video and move on to another problem. This was way more than you needed for that first problem, but it was a good problem to add DVD bonus material to. Let's pause the video here and move on to more problems.